Good evening, everyone. Today I'll be presenting on analysis of predicting Abalone age using machine learning. First thing, we import the data, and then we did some data cleaning using the checking the missing values and checking the duplicates, and we found both of them are 0. We also checked the unique values in each feature using the ununique function, and here is the output table. And basic data exploration is conducted using info function and the describe function. Later we will find that, and the AutoVis library to understand the dataset structure, summary statistics, and the relationship between variables. So let's take a look at the AutoVis library and its outputs. So it gives us some fast visualizations. And for example, we found that length and diameter have a strong positive linear correlation, suggesting that the abalones with longer shells also tend to have larger diameters. And we can also get some findings like that the whole weight, shaped weight, and shell weight are all positively correlated. These weight measurements are likely to increase together as the abalone grows. And from the heat map here, let's see, we can the correlation heat mapping reinforces the observations from the scatter plots. It confirms the strong positive correlations between shell weight, diameter, and rings, as well as between the length and diameter. And here, let's take a look at a noticeable graph in the violin plot here. We can see here are 7 violin plots about the 7 features, and the height feature has a long tail on the upper end, suggesting a right good distribution. Most values are concentrated at the lower end, but some extreme values extend significantly. And we will get this finding in another function later. Here is the describe function. And then here is we check the schoolness using the school function. And then we get the same findings in the previous violin plot. The height from this table we found that the height feature is significantly rise good because this figure is extremely high and compared to the others. So here comes to the encoding part. So why we have to encoding? The sex feature in the dataset is categorical, meaning it represents distinct categories, male, female, and infant, rather than numerical values. Most of the machine learning algorithms work best with the numerical data. Therefore, we need to encode the sex feature into a numerical representation so that the algorithms can understand and use it effectively. Here we use the label encoder function to conduct the label encoding to transform the sex feature. Label encoding assigns a unique integer to each category in the feature. It's simple and clear. And then we check the skewness of the target Y here, and we found that the figure is not very low. So then to get deeper in the details, we use the two-key rule function to detect outliers of the variable Y. So the two-key rule function is called here. Identify outliers in the rings columns of the Abalone dataset. The returned outlier indices are then used to remove those corresponding rows from both the feature matrix X and the target variable Y. So this approach can help us to ensure that the models are trained in the data that is more representative of the typical abalone population, leading to potentially more accurate and reliable predictions. And then we did data splitting in this part. The data set is split into training and testing sets using the function train test split. uh, to evaluate the performance of the models on unseen data. And then we also did the standardization using the function standard scalar. This function is applied to both the features and the target variable to bring them to a similar scale, which can improve the performance of certain algorithms. And then is most important part. Here is the feature importance regarding the 7 features. We can see that the shell weight has a very strong weight, and also the shift weight and height, and a variety of base learner regression models are trained and evaluated. The models are trained on the training data, and their performance is evaluated on the testing data using performance function, which calculates and prints MSE, MAE, and R-squared metrics. So let's see the models here are including the linear regression models such as this one and the lasso and ridge and the elastic net. These are all linear regression models. And then is the KNN, SVR, decision tree, and MLP. So here we call the performance function to get the performance of those model predictions. And then let's take a look at those output graphs and also the MSE, MAE, and R-squared scores. So first, we can say that all the models here are tend to have a high prediction errors for the older abalones. So we can see in the graphs can get a finding. And then the linear regression models are tend to have an R-square, which is very moderate, is like around 50%. For example, we can see this one is 53%, and this one is extremely low, and here is 53%, and here is 38%. So they are not very high, mostly are lower than 50%. And so meaning that the linear models may not fully capture the complex relationships in this data set. And the KNN seems to have a slightly higher performance, better performance than those linear regression models, but not very much. And also the SVR is just that's kind of moderate. And the decision tree did a very bad performance here. It only has 20% of the R square. And the maximum area is also high. And then here is the multi-layer perception, the MLP. It has a 0 score of the R square, and we can see it's just like a line. It's because maybe the model parameterization issues or data itself is just not applicable to MLPs. So here is the end of the coding, and we can get some findings here. Is that maybe the focus should be on developing automated systems using the models that have demonstrated good performance on the Abalone data set, such as the linear models or tree-based models. And these models might offer a good balance between accuracy, interpretability, and the ease of implementation. So while the test models provide a solid foundation, their performance is limited by imbalanced data and difficulty in predicting extreme ages. And then the future improvements should focus on better data collection and age-specific modeling strategies. By addressing these challenges, we can significantly improve the accuracy and reliability of the Abalone age prediction models. Thank you for your attention today.